Question 1. What is the primary advantage of fine-tuning a pre-trained model compared to training a model from scratch for a specific task? Option A. It always guarantees higher accuracy than any model trained from scratch. Option B. It requires significantly less computational resources and data, leveraging existing learned knowledge. Option C. It eliminates the need for any task-specific labeled dataset. Option D. It makes the model architecture simpler and easier to understand. The correct answer is, quote, it requires significantly less computational resources and data, leveraging existing learned knowledge. Here's the explanation. The overview states that fine-tuning allows developers to achieve high-performance models without the immense computational resources, vast amounts of data, and extensive time required to train a model from scratch, as it leverages the strong foundational understanding of the pre-trained model. Question 2. When fine-tuning a pre-trained deep learning model on a new, smaller dataset, what is a common practice regarding the learning rate and why? Option A. Use a significantly larger learning rate to accelerate learning on the new data. Option B. Use a much smaller learning rate to avoid catastrophic forgetting of the generalized knowledge. Option C. Keep the learning rate the same as during the initial pre-training phase. Option D. The learning rate is irrelevant during fine-tuning, as only the output layer is updated. The correct answer is, quote, use a much smaller learning rate to avoid catastrophic forgetting of the generalized knowledge. Here's the explanation. The How it works section states that, often, a smaller learning rate is used compared to initial pre-training to prevent catastrophic forgetting of the generalized knowledge. Question 3. A developer wants to make a large language model, LLM, provide more accurate and up-to-date responses by referencing a proprietary knowledge base without altering the LLM's internal weights. Which technique is most appropriate for this scenario? Option A. Full fine-tuning. Option B. Feature extraction. Option C. Prompt engineering. Option D. Retrieval augmented generation, RAG. The correct answer is Retrieval Augmented Generation, RAG. Here's the explanation. RAG combines an LLM with an external knowledge retrieval system, providing relevant information as context to the LLM within the prompt, without altering the base model's weights. This helps generate more accurate and factual responses. Prompt engineering optimizes the input but doesn't necessarily involve external knowledge retrieval in the same structured way as RAG. Fine-tuning modifies model weights. Question 4. What is the fundamental characteristic that distinguishes embeddings from traditional numerical representations like one-hot encoding or TF-IDF in AI/ML applications? Option A. Embeddings are always higher dimensional than one-hot encodings, making them more computationally intensive. Option B. Embeddings capture the semantic meaning and relationships between objects, representing them as dense vectors where similar items are numerically close. Option C. Embeddings are only used for text data, whereas one-hot encoding and TF-IDF can be applied to various data types. Option D. Embeddings are designed to be human-readable, providing explicit labels for each dimension. The correct answer is embeddings capture the semantic meaning and relationships between objects, representing them as dense vectors where similar items are numerically close. Here's the explanation. The core advantage of embeddings is their ability to encode semantic meaning and contextual relationships into a dense vector space. Unlike one-hot encoding, which treats each item as unique without relation, or TF-IDF, which measures word importance but not semantic similarity. Embeddings place semantically similar items closer together in the vector space, enabling more sophisticated AI tasks. Question 5. A company wants to implement a semantic search feature for its vast product catalog, allowing customers to find products based on conceptual similarity rather than exact keyword matches. Which cloud-native component is essential for efficiently storing and querying the numerical representations that enable this functionality? Option A. A traditional SQL database with full-text search capabilities. Option B. A NoSQL document database for flexible schema. Option C. A vector database or vector store optimized for high-dimensional similarity search. Option D. An object storage service like AWS S3 or Azure Blob Storage. The correct answer is a vector database or vector store optimized for high-dimensional similarity search. Here's the explanation. Semantic search relies on comparing embedding vectors. Vector databases are specialized databases designed to efficiently store and query these high-dimensional vectors, specifically for nearest neighbor or similarity searches, which are critical for finding conceptually similar items. Traditional SQL or NoSQL databases are not optimized for this type of query at scale. Question 6. Which of the following scenarios is not a typical use case where embeddings provide significant value? Option A. Recommending movies to a user based on the semantic similarity of their watched history to other films. Option B. Detecting unusual network traffic patterns by flagging data points whose embeddings are outliers from normal clusters. Option C. Counting the exact frequency of specific keywords in a document for basic keyword density analysis. Option D. Finding relevant knowledge base articles for a customer support query, even if the query uses different terminology. The correct answer is counting the exact frequency of specific keywords in a document for basic keyword density analysis. Here's the explanation. Embeddings excel at capturing semantic meaning and relationships, making them ideal for tasks like recommendations, anomaly detection, and semantic search, where understanding context and similarity is crucial. Counting exact keyword frequencies, like in TF-IDF, is a simpler, statistical task that does not require the semantic richness provided by embeddings and can be achieved with basic text processing. Question 7. A financial institution uses an AI model for loan applications. An audit reveals that the model approves a significantly lower percentage of loans for applicants from a specific demographic group, even though their credit risk scores are statistically similar to approved applicants from other groups. Which definition of fairness is primarily being violated here? Option A. Counterfactual fairness. Option B. Predictive parity. Option C. Demographic parity, statistical parity. Option D. Individual fairness. The correct answer is demographic parity, statistical parity. Here's the explanation. Demographic parity ensures that a positive outcome, like loan approval, is equally likely across different demographic groups. The scenario describes a disproportionate outcome for one group, indicating a violation of demographic parity. While other fairness definitions might also be relevant, demographic parity directly addresses the percentage of loans outcome across groups. Question 8. A company's AI-powered recruitment tool consistently ranks male candidates higher for engineering roles, despite similar qualifications across genders. Upon investigation, it's found that the training data predominantly consisted of historical hiring records from a period when male engineers were overwhelmingly preferred. What type of bias is most likely at play in this scenario? Option A. Measurement bias. Option B. Algorithmic bias. Option C. Confirmation bias. Option D. Historical bias. The correct answer is historical bias. Here's the explanation. Historical bias reflects societal biases present in real-world data, which the AI then learns and perpetuates. The scenario clearly indicates that the training data reflects past discriminatory hiring practices, leading to historical bias in the model's outcomes. Question 9. Which stage of the machine learning lifecycle is not times a primary focus for applying mitigation strategies to reduce bias in AI systems. Option A, pre-processing, adjusting training data. Option B, in-processing, modifying the training algorithm. Option C, post-processing, adjusting model predictions after training. Option D, model deployment, after continuous monitoring shows no issues. The correct answer is model deployment, after continuous monitoring shows no issues. Here's the explanation. Mitigation strategies are typically applied at pre-processing, in-processing, and post-processing stages. While monitoring is crucial during deployment, the statement, "after continuous monitoring shows no issues," implies that mitigation isn't a primary focus, times no issues are found. However, fairness is an ongoing concern, and mitigation should be considered if issues arise during monitoring. The other options are direct stages for applying mitigation techniques. Thanks for watching. Please subscribe to my channel.